So welcome to lecture 10. I'll just get right into it. So last time we defined the spectrum and the resolvent set and the spectrum and also the resolvent of an operator. So let's just continue on from there. So let me just start with a lemma. Lemma. So suppose that B1, B2 are a reflexive perfect pair, and T is a densely defined operator that is closed in B2. Then T inverse is, so this in particular means injective, is bounded in B2 if and only if T inverse adjoint is bounded in B1 and T star inverse is equal to T inverse star. Okay, so that's not something very deep, it's just something that you can verify. So this leads us now to the following proposition, because we also want to understand how the spectrum of the adjoint relates to the spectrum of the original operator. So let B1, B2 be reflexive again. So that's what we need to talk about, these adjoints with respect to the pairing, if you recall. So T is a closed operator in B2 that is densely defined. Then, so from the previous proposition, we know that we have a closed densely defined operator, we have a reflexive space, so its adjoint is also closed and densely defined, right? So then the spectrum of the adjoint is equal to the spectrum of T conjugated. This is the complex conjugate, so I'm going to take to writing, so I don't know what the best notation is, but for sets, I'm just going to write this. The resolvent set of T star is equal to the resolvent set of T conjugated, complex conjugated. Okay, and that's the statement. So the proof of this, so how would we show this? So it suffices to show that whenever zeta is in the resolvent set of T, we obtain that zeta bar is in the resolvent set of the adjoint. Okay? So why is this true? Well, let's write it out. So we have zeta minus T star UV. So if we write this out, so in the T slot we get the T star, but in the slot here for the conjugation of this number zeta, we obtain precisely zeta minus T V. Okay. So this tells us, so what does this tell us? This tells us that zeta minus T adjoint is precisely equal to zeta, it's precisely equal to this. And so by the previous lemma, okay, so maybe I'll write this here. By previous lemma, so what it means for what it means for something to be invertible. So if this is invertible, so we have that zeta minus T is invertible, so zeta minus T adjoint is also invertible, and we know exactly the expression, so that gives us that so by lemma we get that zeta minus T star equals zeta bar minus t star invertible. And that precisely means that the complex conjugation of zeta is in the resolvent of t star. Okay, so it's a symmetric argument now if you start with t star, because it's a closed operator, t star star is again equal to t. And so we obtain the conclusion in the opposite direction, right? And then that gives us the equality for the resolvent, and hence it gives us the equality for the spectrum. Okay, so let's have a look at a few examples just to polish our understanding. So suppose we have A being a matrix, so n by n matrix. Then we only have, the spectrum is only point spectrum. Okay, and these are precisely generalized eigenvalues. Well, I say generalized, I mean they're eigenvalues, but you know the eigenspaces might be more than just those corresponding to the eigenvalues, right? Because you could have a block matrix. Okay, so a very important example that we've already seen are self-adjoint operators, and they have a certain, so the reason for the spectral theory, for the spectral theorem, namely this ability to integrate over the real line, is really because for self-adjoint operators the spectrum is real, right? So let's take an operator. Yes? Yeah, but what I'm writing when I say generalized eigenvalues is that you might have eigenspaces that are generalized. Yeah, it's just to emphasize that it's not just, so the point is that the point spectrum of the operator are not just the eigenvalues, right? Of course, we say that they're eigenvalues, but one has to be careful because when we think about eigenvalues, we often think about eigenspaces, but it's important to think about the whole generalized eigenspaces. So it's just to somehow emphasize that I've written in brackets generalized, because it's not really generalized, it's just, of course, they're eigenvalues, and then the corresponding eigenspaces may contain generalized eigenspaces, right? But it's just to drive home that point that I've written that. Okay, so let's take an operator T, which is a closed operator from H to H that is self-adjoint, right? So every self-adjoint operator is necessarily closed, right? I.e., so T is symmetric. Recall what that means. Such that T is equal to T star. So if T is equal to T star, I mean T star is always closed, and so this has to be true. Okay? That it's closed and densely defined. Okay. So then the spectrum of this operator is real. And so there are two things here. Then, so the first thing is that the spectrum is real, and the second thing is that there are these so-called resolvent estimates. And we will see that these resolvent estimates are key when we're dealing with unbounded operators, or the spectral theory of unbounded operators. So what are these resolvent estimates? So the resolvent estimates are for zeta not in the real line. We have that, so if the spectrum is real, then certainly everything outside of the real line is in the resolvent. So we have the inverse, so this is invertible, and this is going to be bounded by 1 divided by the imaginary part of zeta, norm u. Okay, so these are what we call resolvent estimates. So let me quickly run this by you. So how do we prove this? So for one, so take some zeta in the complex plane, subtract r. So what we have is TU is equal to UTU. But we also know that if we just take TUU and we conjugate, so if we just swap the T and the U, that that these two relations hold, right? So the second relation always holds. The first relation comes from self-adjointness, okay? So this is from the self-adjointness condition, and this is always true. So maybe I should have written it in the other order, okay? So what that tells us, that TUU is real, okay? So then zeta minus TUU is exactly equal to zeta u squared minus TUU. Okay? So, I mean, now the imaginary part of this expression is 0, right? So I can take the imaginary part of the expression here. So the imaginary part of zeta minus TUU is precisely going to be, well, it's actually, right, so it's, so it's equal to the imaginary part of zeta norm u squared. Okay? So now what we have is we have u squared is now less than or equal to 1 over the imaginary part of zeta, imaginary part of the modulus of the imaginary part of zeta minus TUU. But of course, the imaginary part is going to be bounded by the whole expression. Okay, so now from this we get that this is 1 on imaginary part of zeta, zeta minus TUU. And of course, now this is going to be less than or equal to 1 on the imaginary part of zeta, zeta minus TUU. Okay? So now, I mean, from this, first of all, we have, so we have that this is, so we can cancel the u here, so we get that, so from this we deduce that u is less than or equal to 1 on imaginary part of zeta, zeta minus TU. So that's the first thing, and so in particular this means that this is injective. Okay? Okay. Now, the second observation is, remember from the result that we mentioned last time, that the range of the adjoint operator, the annihilator of the range of the adjoint operator is the kernel. So in a Hilbert space, so since the range of zeta minus t perp is equal to the kernel of zeta minus t, and this relation holds within the Hilbert space. So this is really the orthogonal complement, right? So when we have a Hilbert space, we have given some subspace, we have an orthogonal complement, and then we can split the space. So then we get that H is equal to the kernel of, sorry, this is the kernel of the star. Okay, so let me just see. So So okay, so we have to simultaneously do this for zeta, and we can also do it for zeta replaced by so we can um, so I should say similarly, we have that u is less than or equal to 1 on imaginary part of zeta bar minus t of u, right? Because all we assumed about the zeta was that it was outside of the real numbers. So then we get that h is equal to the kernel of zeta minus t plus the range of zeta bar minus t adjoint, but of course the adjoint is equal to itself, and this is closure, right? Because this is the range of zeta minus t annihilated is equal to this. So now if we annihilate this again, we have the closure of the range of zeta minus t, okay? And this is again equal to kernel of zeta bar minus t plus the range of zeta minus t closure, okay? So but both of these spaces, so kernel of zeta minus t equals the kernel of zeta bar minus t is equal to 0, which means that it has dense range. Zeta minus t has dense range. And that, along with the estimate, means that zeta is in the resolvent set of T. Okay, and we already have, so two immediate from calculation. All right. So in the end, what we really need is to, in the end, what we obtain is that self-adjoint operators have real spectrum, but they also satisfy a very nice resolvent estimate, and that's really what's necessary in order to move forwards and do things, right? So let me also just say very quickly, as a third example, so what am I writing? 1, 2, 3 for examples, or A, B, C? What am I writing here? 2, 3, yeah. So 3, if T is non-negative self-adjoint, i.e. TUU is greater than or equal to 0, then that means that the spectrum of T is in 0 to infinity. Okay, so similar calculation yields that. So, i.e. Laplacian I equals 1 to n partial I squared on Rn is non-negative self-adjoint. And it's important to be careful here because we might not just have eigenvalues. And the point is that the spectrum now of this is the real line. Okay, so it could really be that we don't have just point spectrum. But then this leads us to asking the following question. When do we have pure point spectrum? Okay, so we saw this in the case of matrices. Now the question is, when might this happen in the beyond the matrix situation, right? When might this happen in a situation where we're in infinite dimensions? So for that we need to talk about compact operators, right? So let's start with the definition. So T is a bounded operator is compact. It's called a compact operator if for all balls of radius r in the Banach space B, the image of T acting on this ball of radius r is pre-compact. Okay, so this is for all r. Okay, so maybe I should say remind what this means. So this as a set is compact. Okay. So an important observation, so remark, maybe this should be a lemma, is that T of B is B in B compact, and S is some other bounded operator, just a bounded operator, then TS and ST are compact. Okay, so compositions of operators with compact operators result in a compact operator. So why do I talk about this? So let's have a proposition. So one, if this is a compact operator, then that means that the spectrum of T is just pure point, and consists of isolated points only accumulating at 0. Okay? So I mean so that means that, you know, we have, maybe I'll, oops. So we have, you know, points. So the only accumulation point is going to be, so maybe there's lots and lots as we approach 0, but the only accumulation point is going to be 0, right? So that's the first thing. And the second thing is that if we have a closed operator and we have some element in the resolvent set such that zeta minus T inverse is a compact operator, then we have that the spectrum of T is lambda I, oops. So we just have some countably many isolated set of points. Yeah, I should have said that accumulating at 0, and the eigenspace of lambda is finite dimensional. Okay, so the generalized eigenspace. So here, maybe I'll write gen eigenspace. Okay, so so we have if we're in the closed situation and we have a compact resolvent, then the spectrum of the original operator that we're interested in, the closed operator, is a set of isolated points. The generalized eigenspaces corresponding to lambda I is finite dimensional, and only accumulation point is at infinity, right? So there are no finite accumulation points. Moreover, if zeta prime is in the resolvent set of T, then we also have that zeta prime minus T inverse is a compact operator. Okay? So how does this help us? Well, I mean, this entire sort of treatise is guided by what we encounter in the wild, in the land of differential geometry. So what's the corollary here? So let D be a differential operator of order M, E, which is elliptic, where E is some bundle over M prime, where M prime is compact, and the boundary of M is empty, right? So boundaryless. So now, if the resolvent set of D closure, so there's only one closure for D, right? Because we're in the boundaryless situation. So if the resolvent set of the closure of the operator is non-empty, then it means that the spectrum of D is discrete in the above sense. So discrete here means that it's countable with only infinity being the point of accumulation, and generalized eigenspaces are finite dimensional and smooth. Okay, so why is this true? So we recall that, of course, that D prime is equal to D max equals to D min, right? Well, you could have so the question is, how can a subspace be smooth and non-smooth? Well, the domain of this operator, as I'm about to write, is HM. So you could easily, a priori, have only Sobolev regularity sections. There's nothing to say that your sections are going to have high regularity. Precisely, a subspace in this setting is called smooth if the sections are smooth. Right? So we're always dealing with function spaces. So the question really is, what is the regularity of the function space or the section that we're dealing with? Okay. So recall that this happens since M prime is compact without boundary, right? So maybe I'll write M prime there, without boundary, okay? And then elliptic regularity, this is a proof of the corollary. The proof of the proposition you can find in Cato. I won't go, we have to make a decision of what the important things to prove are, and I think the example is more important than the abstract theorem because that can be accessed anywhere. Of course, you can probably find this anywhere too, but just to have seen it in application, I think it's more of a significant thing to do. Okay, so elliptic regularity gives us the domain of this operator, right? So it tells us that this is precisely HM, ME. So what do we have? We have HM, M prime E. This is certainly a subspace of H1 M prime E, and this embeds compactly into L2. right? So the compactness of this embedding is again a consequence of the fact that we are on a boundaryless, well, not a boundaryless, but we are on a compact manifold, okay? Since M prime is compact. So now, if zeta is in the resolvent set of D, then we have zeta minus D inverse is going to map us from M prime of E into the domain of the operator, which is HM M prime of E. And then, so if we factor this, so we're interested in this as a L2 to L2 map. But we factor it through the embedding. Okay, so this embedding, this embedding of HM into L2 is compact because the composition of a bounded operator with a compact operator is compact, right? So the embedding of HM into L2 is compact. So this is compact, and that implies that zeta minus D inverse is a compact operator. And then from the proposition we obtain that from the proposition we precisely obtain the required result, right? And proposition gives us discrete spectrum with finite dimensional generalized eigenspaces. Good. So the smoothness, so if, I don't know, phi is in generalized eigenspace of D, then one can show that phi is in H L for all L because it's in the generalized eigenspace, and that means that phi has to be smooth, right? The intersection over all the Sobolev spaces lands us in the smooth world. Okay, so that's the proof. All right. So I just want to sort of highlight that a lot of this abstract theory that I'm going to be talking about is very much guided by this application to differential operators, right? So it might seem sort of abstract at first to talk about these sort of things, but it's very natural. So on the boundary, typically our boundary is going to be a compact manifold without boundary, and we have differential operators on there, and so we we automatically have very good properties of these operators. Okay, so moving along, I want to broach another slightly abstract topic, which will become of importance in what we're about to do. And that's Banach-valued integrals. So there's a very large theory of, yes? HL M prime E for all L. That's the point. So smooth functions or smooth sections are contained in the intersection over all Sobolev scales, and that comes from the Sobolev embedding theorem. Okay, so Banach-valued integrals. So there are lots of very complicated integration theory in the Banach space setting, and we're not going to need that. So in terms of what we are going to want to integrate, it's going to be holomorphic functions, right? So we just really need to make sense of continuous functions into Banach spaces. So let's start with a real valued function first. So we have a real valued function AB into B. And so the definition of, so the Riemann integral in this case, so the Riemann integral is exactly what you expect, right? It's just taking a to b of f of t dt is defined as taking the limit as n to infinity. So the limit is now taken with respect to the Banach space norm, j equals 1 to n minus 1 of b minus a divided by n. So whenever this converges, right? So we say it's a Riemann integrable when this converges, j b minus a on n. Okay, so I'm sure this name has a method, trapezoid rule or something. So the Riemann integral is defined to be this. So the limit exists by continuity of f. So we just need to show, that this sum n minus 1 of b minus a on n f of a plus j b minus a on n, using continuity, that this is Cauchy in B, and completeness then gives us the limit. Okay, so that's the first. So maybe this should really be written as a definition. So now now we look at f from the open interval a into b, continuous, and then we define a to be f of t dt to simply be equal to limit a prime tends to a of a prime to b. Now it's a closed interval, f of t dt, when the limit exists. Okay. And the point is that when we have this norm integrability, we have that the integral itself is integrable, and this is going to be controlled by the norm, the integral of the norm. Okay, so it's like a triangle rule, the integral sense. Okay, so now the third thing we want to look at are contours, right? So gamma is a contour from the interval a to b into omega, which is some subset of C. So this is a contour. It's continuously differentiable. And we take some function f from omega into b continuous. Then the Contour integral of f is simply defined to be the integral a to b of f composed with gamma of t gamma dot of t dt. Okay, so we can these notions are readily extended to piecewise continuous differentiable as in the real or complex scenario. Okay. So in particular, what's really important is that with respect to this notion of integration, we have the following, right? So suppose that we have okay, so maybe this should even be a lemma, but suppose we have so I should say with this integrand many results of C valued holomorphic functions hold for b-valued holomorphic functions. So, i.e., f from omega to be holomorphic, then f of some point omega in, so for a curve that envelopes the value omega, we have the Cauchy integral formula, right? Z okay, so we have this Cauchy integral formula. Just an example. So let's just go back to the Cauchy integral formula for just complex valued objects. So what do I mean by that? So let's just consider classical Cauchy integral formula, i.e. for b equal to c. So what I want to do is I want to interpret this in a slightly different way, right? So I should say that, this is a contour that goes around counterclockwise around omega, right? So this is what this contour is, okay? So, so let's consider the case b is equal to c, and now I want to consider, let mw, which is now, I'm going to consider it as an operator that maps complex numbers into itself, and I'm going to define mw of z is equal to just omega z. Okay, so what is the spectrum of this operator, right? So the spectrum, so we have lambda in the spectrum of m omega, so we know that it has to be point spectrum because it's just a matrix. We can think about it as a matrix. So this happens if and only if there exists a non-zero z such that mwz equals lambda z, and so that's if and only if there exists a non-zero z such that wz is equal to lambda z, and this is if and only if omega is equal to lambda. Okay, so the only so the spectrum purely just consists of the point omega. Okay, so I want to turn this Cauchy integral formula around. What we typically see this Cauchy integral formula as is that fix a holomorphic function, and we can recover the value of this holomorphic function at this value omega by an integral of this form. But I want to consider it in a different way. I want to say, give me this point omega, and I want to consider all possible functions in a neighborhood of this omega, right? So in our language, let omega be a neighborhood, open neighborhood. So this is, I should really say, reinterpretation, right? Reinterpretation of Cauchy integral formula, right? So let omega be an open neighborhood of omega, which is equal to the spectrum of this operator m omega, and f now is just a function from this open neighborhood of omega, which is the spectrum, to the complex numbers. and let's take some gamma that envelops the spectrum inside omega. Okay, so I just want to just really drive this home. So we have this, I don't know, this omega. We have, this is the spectrum of m omega, and well, we have a contour parameterized counterclockwise. Okay, so let's just define this whole idea of enveloping something to mean parameterized counterclockwise. Okay, so now let me impressionistically write this. I'm going to write the function of the operator itself acting on Z. So what is this? This is going to be, you know, I want this to be m of f at the point W acting on Z. And so this is equal to f of W acting on Z, which is equal to, so I think I forgot the normalization here. I'm sorry, 1 on 2 pi iota, right? So, and this is exactly what? This is 1 on 2 pi iota of f of zeta divided by zeta minus W d zeta. But I want to write it slightly differently again. So this is 1 on 2 pi iota of f of zeta, and now this is zeta minus, okay, so there's a multiplication by a z here, right? So this is zeta minus, this is zeta minus omega of z, but, oh, sorry, inverse, d zeta. But let me rewrite this again. So this is, again, I can write as 1 on 2 pi I f of zeta, zeta minus, now m omega inverse acting on z d zeta. Okay, because that was the definition of my operator. So what do we find here? We find that if f is equal to the identity, then we find that f of m omega is precisely just equal to m omega, right? That's what we get. It's just omega itself. If f is equal to 1, the constant function 1, then f of m omega is equal to the identity. So the reason I wrote this last line is because I want to really see this as a resolvent, right? So you can see here now that the spectrum is this point. We have a curve wrapping around the spectrum, and what we obtain in the denominator in the Cauchy integral formula is we can reinterpret as actually a resolvent of an operator, okay? If we see it from this point of view. So this is very suggestive, okay? So this is suggestive, and the first thing we're going to look at is the case of bounded operators. So let's start with the proposition. Let T be a bounded operator on a Banach space. So the first and very important consequence of this is that the spectrum of the operator now is compact. It's a compact set. So now let omega in the complex plane be an open set, and let f be a function from omega into the complex numbers holomorphic. Then the Ries-Dunford functional calculus is simply, so we take, let gamma be a curve, I don't know, C1 curve enveloping spectrum of T. So this is now a compact curve. So it's a compact curve. So I should say C1 finite Dunford, Rees-Dunford. So this is a finite length curve enveloping the spectrum of T. And so we can define f of t of u as 1 on 2 pi I of this curve, f of zeta, zeta minus t inverse of u d zeta. Okay, and this is now a bounded operator in B. Okay, it's bounded because, of course, this is a finite length curve. So if we take the norm of this operator, it's going to be bounded against the length of this curve, and so it's a holomorphic function, so it's going to take a finite value on the curve because it's a finite length. And of course the resolvent is also a holomorphic map, remember? So that was the first thing I said. So that also takes a sup, right? It attains a maximum along the curve. So this is a bounded operator. So let me just draw this picture again. So, so the spectrum of T now could be this. So it could be just this whole blob in here, right? So this is the spectrum of T. Yes, parameterized counterclockwise. So winding number 1 parameterized counterclockwise. Okay? Yes. So so maybe the spectrum splits up into 2 components of this form, and my omega might be this set here, and a curve would look like this. So this would be my gamma. So so what does this functional calculus satisfy? So it satisfies, so this satisfies if, when it's the identity, f of t is equal to t. When f is equal to 1, we get that f of t is equal to the identity. Alpha 1 f1 plus beta, alpha f1 plus beta f2 is going to be equal to, of t is equal to alpha 1 f1 of t plus beta f2 of t, and the composition, and f1 f2 of t is equal to f1 of t f2 of t. Okay, so amongst other things, right? So so f1 composed with f2 of t is equal to f1 of f2 of t, etc. Right? So it satisfies lots of nice properties. So remark, the map taking us from f to f of t, which takes us from the holomorphic functions in omega to the bounded operators in B, is a homomorphism into a commutative subalgebra. Right? Because functions commute, and so the functional calculus also commutes. But the operator t itself I mean, it's not going to commute with lots of things. Okay? So this tells us a story of what has to happen in, or what can happen in the world of bounded operators. But of course, we have to deal with unbounded operators. Okay, so the operators that we deal with certainly will not have spectrum that is contained in a compact region. For instance, the Laplacian on Rn is the entire positive real line from 0 to infinity. So somehow, in order to develop this sort of an extension to the unbounded world, what we really need are some sort of estimates, right? And that's precisely what we saw for self-adjoint operators, right? Self-adjoint operators have this nice resolvent estimate that tells us that as we push the resolvent out to infinity, the imaginary, so we're controlled in terms of 1 divided by the imaginary component. So things decay as we go out towards infinity, right? So we have to somehow harness that information when we try and develop something in the unbounded case. But before we go head first into that, let's just have a quick look at an example in the closed operator situation, right? So closed operators. So this is the first take on closed operators. So this is a very important proposition, right? So let T be a closed operator. And suppose that the spectrum of T is a disjoint union where the omega 1 is this is enveloped by I don't know, a rectifiable curve. So, well, maybe I'll just say a curve with a piecewise continuously differentiable curve. Okay. Then P of U defined by 1 on 2 pi iota of this gamma of zeta minus T inverse continuous differentiable curve with compact image. So in particular, that means that gamma 1 is compact, omega 1 is compact, right? So this well, you're right. I mean, okay, so the yeah, that's true. That's true. So it's always true that it has a compact image if it's a closed curve. So the point is that we could also have non-closed curves. So we could still, for instance, we could talk about omega. So okay, that's a good point that's been made. So the point is that yes, the notion of enveloped can include open curves when we generally talk about these things, because the part omega 2, for instance, it is enveloped by a curve because I mean the part, it could be a piece that goes out infinitely in the complex plane, and we need to have a curve that somehow infinitely extends out and it's really cutting through the spectrum at infinity. But we'll talk about that a little bit more later, because that's not so important right now. Here the point is that this is the part omega 1 is compact, and the curve is really a curve in the open interval. It's a curve in the closed interval a to b mapping into the complex plane. Later on we have to look at curves which are in the open interval a to b. Okay, but here we're just in the, so maybe I should really, yeah, so let me really point that out with, so this is really gamma from A to B into C. Okay, so then this fixes the problem for what we want to say right now. Okay, so anyway, so this device, this definition, so this is certainly a reasonable definition because the image of gamma here now is compact. So the resolvent is holomorphic, it takes a finite value. This is a bounded map. But it's more than a bounded map. Then this defines a projection. And B is going to be split up into P of B plus 1 minus P of B, as we've seen before. Okay? U of zeta. What? No. No, it's not applied to zeta. This is zeta minus t inverse of u, right? And u is, well, u is an element of the Banach space. Sorry, u is an element of the, u is an element of the Banach space. The resolvent gets applied to u. This produces an element of the Banach space. And then we're integrating over the zeta. Okay, so this defines a projection, and the operator T now restricted to P of B is actually an operator from this subspace back into itself. Okay, and the reason for that is that, as I said, when we have functions of these things, I mean, when we have these resolvents appearing, if an operator commutes with the resolvent, then it commutes with any integrals involving the resolvent, right? So this is now a bounded operator. The operator T restricted to 1 minus P of B takes us from 1 minus P of B to 1 minus P of B. And the spectrum of T restricted to P of B is equal to omega 1, and the spectrum of T restricted to 1 minus P B is omega 2. Okay, so this is a very important proposition because it gives us an indication of how to use contours or contour integration to split up a space with respect to an operator. Okay, and that's what we really need to do when we, I mean, remember we're really guided by things like this check space and so on and so forth, which we've defined. But we want to understand this space in terms of the operators that are given to us. So we have to be able to decompose the spaces on which an operator might act with respect to information coming from the operator itself. And here we're making that information precise. That information is precisely contained in the spectrum of the operator. So here is a picture of what might happen. So this is omega 1 and maybe this is omega 2. This is a unbounded piece. And we have maybe the curve gamma through here. And we're just integrating now around this curve, around here, right? It separates the spectrum, and then we obtain operators here, and we have an operator here. Oops, this is 1 minus PB. Okay, so the goal now, extend this to a wider class. Okay, so that's really the goal. So maybe I should just also say something very quickly here. So okay, so so maybe this is an exercise. So if M is again a matrix, I don't know, n by n matrix, then the spectrum of spectrum of M we've seen before is going to be some finite number of points, lambda n say, and each of these we can draw a contour around them, right? So each of them we can draw a contour. So maybe these points are going to be so we have some contour lambda this is gamma I to the lambda I, and the okay, so the point is that pi of u, which is now I'm going to write as gamma of gamma I of zeta minus m inverse of u d zeta is the projection to the generalized eigenspace of lambda I. In fact, you could recover, by this method, you could recover the Jordan decomposition theorem. Okay, the Jordan decomposition is simply by writing out this integral, and then you can decompose the operator into these spectral subspaces. Okay, so this yields the familiar Jordan decomposition. Okay. All right, so let's press on. So in order to extend all of this, so our goal is to extend this to a wider class of operators. And in order to extend this to a wider class of operators, we need to have some extra information about the resolvent and the way the resolvent decays at infinity. Okay, so so for bounded operators, we've seen that this is taken care of by the fact that the spectrum is compact. So we have very nice decay at infinity. So we now need to institute that or ask for that when we deal with closed operators, right, to move on. So okay, so let me make some definitions. So let T be a closed operator on a Banach space, and define the open and closed sectors and bisectors. Okay, so so the S omega is we'll define to be the zeta, which are the complex numbers, non-zero complex numbers, such that the argument of zeta is less than mu, or the argument of minus zeta is less than, sorry, did I write omega here? This is mu. Oh, mu. And I'm going to write S mu as equal to just the closure. Okay? Yeah, okay. So maybe I'll just write bisectors, not sectors, right? So, well, okay, maybe I should also say something about sectors. So, the sector then, S mu plus, is equal to S mu naught intersect the zeta in C such that the real part of zeta is positive. Okay, so this is the plus minus, well, positive negative sectors, so plus minus the real part. Okay, all right, so with this, let me define now the notion of a bisectorial operator, right? And sectorial also. So for this, for bisectoriality, we require that omega to be less than pi on 2. So let omega be less than pi on 2. It's the closure of this. So let omega be less than pi on 2 and let T be a closed operator that's densely defined. Suppose that the following hold. The spectrum of T is contained in the closed sector S omega, bisector, sorry. And the second point, so for all mu greater than this, so all mu contained in this omega less than pi on 2, there exists some constant, C mu, such that whenever I have some zeta that's not in S mu, we have the estimate zeta of zeta minus T inverse to be bounded by this C mu. Okay? Sorry, this is S minus naught. Sorry. This is S minus naught. Okay. So this is the notion of a bisectorial operator, and the condition number 2 is really what takes care of the resolvent bounds that we require, right? So such an operator is called bisectorial or omega bisectorial. Okay. If the spectrum of T is actually in S omega plus, then we say it is sectorial. So remark, for sectoriality, we can allow the omega to be greater than pi on 2, but needs to be less than pi. Okay, but this is not a situation we're going to encounter. Well, that's not true. We do need to encounter it somewhat, but I'm going to throw that under the rug because it's not so important, right? Okay. So an important thing to outline is that if B1, B2 are reflexive pair, then when T is bisectorial, or sectorial, then, so I should say I should quantify this because it's important, right? The quantification is important. Then T star is, well, yeah, so I should, okay, densely defined. So this is, when I say bisectorial, I'm always assuming dense definedness, right? Because that's in the definition. So the adjoint is now also densely defined, obviously, is also omega bisectorial. Right? So this is not a hard consequence. I mean, this just comes down to the fact that we already have seen how the resolvent set of the adjoint operator relates to the resolvent of the original operator. And from that, we could also deduce the required resolvent estimates for the adjoint from the original operator. Okay? So let me just maybe draw a picture of all the things that are happening now. So we take the complex plane. We have well, we have the two bisectors, I guess. Yeah, I'll draw that in yellow. So this is an open bisector, and the spectrum of this operator could be, I don't know, maybe there's some isolated blobs. Right, so this is the spectrum of T. And now, okay, so now we can look at a slightly larger sector. So this is the S omega that we have. So this is the closed set, and now we can look at maybe a slightly larger sector which is open, not containing zero. Okay, so this is an angle omega, and this is an angle mu. Okay, so this is S mu 0. And so out here, what's another color? Out here we have zeta minus t. So this is certainly in the resolvent set now, being less than or equal to C mu. Okay, that's the picture. All right. So now we want to start taking functions of these kind of operators. Okay, that's what we want to do. So again, we want to be motivated by the Cauchy integral formula. So this is really at the heart of everything. But let's define some function spaces first. So I'm going to define H holomorphic infinity functions on S mu naught to be f from S mu naught to C holomorphic and bounded. And a very important function class for us is this psi class functions, right? These capital psi class functions on S mu naught. So this is the definition. So these are functions psi which are in the holomorphic infinity S mu naught, such that there exists some alpha, and some constant C that is finite, such that psi of zeta is controlled by constant times the minimum of zeta to the alpha and zeta to the minus alpha. Okay. So, well, example of psi class function. So psi in psi mu naught. So psi of zeta equals zeta on 1 plus zeta squared. Well, maybe I'll just give functions. So zeta maps to this, or zeta maps to, say, zeta to some power of beta e to the minus zeta, etc. Right? So these are lots of functions. So these are functions that decay at 0 and at infinity. In some sense, you could think of these as being something reminiscent of a Schwartz function, but complex value, right? Or holomorphic, holomorphic Schwartz function, right? In some sense, you, yes? Where is the quantifier? I mean, this is for all zeta in the domain of the function, which is S mu naught. It's inside. I mean, otherwise it's a trivial statement, right? Yes, because otherwise it's trivial, right? Otherwise you can always find, I mean, then everything is in there. Right? So, yeah. Okay. Now let me give you a description of how to define a function. Right, so define for psi in psi s mu naught, define psi of t of u as being equal to 1 on 2 pi I. So now I have to talk about what this contour gamma is, right? This is now an unbounded contour, psi of zeta, zeta minus t inverse of u, d zeta. So let me draw the picture again that I had before. Maybe I should just copy and paste it actually. So now I have the spectrum maybe here, and okay, so this is my S omega, so this is omega, S omega. Now let me have my large S mu in here. So this is S mu naught. Well, yeah, okay. I think it's visible where this naught is. So now where is this contour? So this contour now comes out from infinity to 0. It cuts through 0. So that's the first thing. And then it goes out to infinity here. And then it comes back from infinity to 0. And then it heads out to infinity. Okay, so my so this is some curve with some value mu. So this is some sector. This is the boundary of some sector mu. And this is the right parameterization, right? So let me write out what this is. So this curve gamma is t e to the iv such that we come from infinity to 0. And then we go from minus t e to the negative iv from 0 to infinity. And then we go from minus t e to the iv from infinity to 0. And then we go from t e to the negative iv from 0 to infinity. Okay, so how do we make sense of this? Well, you would write this integral by cutting this off at some value epsilon here, right? Oops. You would cut this curve off at some value epsilon and 1 on epsilon, and then you would take the limit. Okay, so this is what we talked about right at the start when we talked about Banach valued integration. So so that's how you make sense of this. But the point is that this is an absolutely convergent integral, right? This is an absolutely convergent integral due to decay of psi and resolvent estimates. For bisectorial T. So what we have, we have that psi of T. So of course when we take this integral, we're really, I mean, this convergence is in the strong operator topology. This is for a fixed U that we define this integral. But then of course we find that this is a bounded operator, so this is going to map, say, B to B, oops, with some norm that depends, of course, a priori on psi and T against U. Okay. So, yeah. Unfortunately, we only have a couple of minutes, so maybe it might not be a good idea for me to persevere further. Let's see. Well, maybe let's just write down this last proposition so we can conclude this. Okay, so the proposition, very quickly. So this that's true. So put a U in there. So I mean, this is also so now it's no longer the operator norm. Yeah, because okay. So so this is a map from psi of S mu naught to B of B, and it's an algebra homomorphism. So maybe it's wrong to call it an algebra. I should just say it's a homomorphism because, of course, in how we've defined the identity is not in there, right? So if the operator S commutes with the resolvent for some zeta in the resolvent set of T, that means, so what does that mean? So that means that S zeta minus T inverse is contained in zeta minus T inverse of S, right? Because these are unbounded operators. So S I'm not assuming is bounded. Then S commutes with psi of T, okay? So I think this is called the bicommutator. We have a spectral mapping theorem. So the spectral mapping theorem tells us that psi of T, the spectrum of psi of T, is equal to the psi of the spectrum of T. And a very important thing that I want to point out is that if B is reflexive, then we have that B is equal to the kernel of T plus the closure of the range of T. Okay, and that's of course not an orthogonal sum. Okay, so I won't really get into the guts of this. Let me just quickly say 1, 2, 3 readily verified. let me just give a hint of what happens for 4. So we define B naught equals to, is the set U in B such that the limit as n to infinity of 1 minus I n t inverse exists. We can talk about this because remember, along here, along the imaginary axis, if we read off these resolvent estimates, we have uniform control as we approach 0. Okay, so in some sense it's saying that we can cut through 0, right? The resolvent estimates are nice. So we can ask for this limit to exist. So there's a U here, I'm sorry. And then the projection, then we can define a projection from B naught to B naught by the expression P of U is equal to limit n to infinity of 1 on in 1 on in minus t inverse of U, which is readily verified to be limit n to infinity of 1 minus int of U inverse. Okay. So that might not actually be true, the second statement I wrote. So let's actually get back to this next time, because I think I'm going to go over time. There's a little problem with the numerology here. So let me give the proof of this next time. Okay, so forget I said anything about it. So I just have to have a look in that again, because this, what I have here does not look quite right. So next time. Okay, thank you. Are there any questions? If not, let's wrap up, and I will see you next Monday.